Okay, so this is now tutorial sheet 2. You finished tutorial sheet 1. Question 1. If a person asks you to buy 500 coffee sweets, how do you count the sweets using the concept of counting by weighing? Now, 500 sweets. If you want to buy 500 sweets and you want to start counting each one of them one by one, that wouldn't be too, like, it would be a sheer waste of time. Okay. Instead, what you are going to do is you are going to measure the mass of one sweet. So if you know the mass of one sweet, let's say one sweet is giving you, say, 2 grams, then you are going to say, what of 500 sweets? How much weight are they going to give you? So let's say 500 sweets are giving you 1000 grams. So just measure 1000 grams of sweets. Then you'd have estimated that you have got 500 sweets. So that is the concept of counting by weights. We are good?
Yes.
Okay. B. Explain why atomic mass on the periodic table are not whole numbers. Now, because most elements exist as isotopes, say hydrogen itself, you have got hydrogen 1, got hydrogen 2, you have got hydrogen 3, you have got deuterium, tritanium. So, all these, when you are finding the mass, the relative atomic mass or the relative masses on the periodic table, those are actually average masses. So when you're talking about average, you always expect to have decimals because it's not the mass of one element, but the average mass. That's why it is that the masses on the periodic table are decimals. Part 3. An element consists of 1.40% of an isotope with mass 203.973 atomic mass units, 24.1% of an isotope with a mass of 205.9745 atomic mass unit, 22.10% of an isotope with a mass of 206.9759 atomic mass unit, and then you have got the 52% with that mass. We want to calculate the average atomic mass. Now, the average atomic mass or relative atomic mass, you have got four isotopes here, be given by mass 1 multiplied by abundance 1 plus mass 2 by abundance 2 plus mass 3 by abundance 3 plus mass 4 times abundance 4. And this will give us the first mass, that is 203.973, multiplied by the percentage abundance, which is 1.4. Now that's the percentage, so divide by 100. And then plus the next one, the next mass is 205.745. Multiply that by the abundance, which is 24.1. Also divide by 100. And then plus the next one, the next mass, that is 206.9759, multiplied by the abundance, which is 22.1, divide by 100. And then plus also the next one, the mass is 207.9766, multiplied by the abundance, which is 52.4, divided by that also by 100. So this is what we are going to be able to work out. Let me just get to punch everything here. 203.973 multiplied by 1.4 divided by 100. Then we are going to have plus 205.745 multiplied by 24.1 divided by 100. And then plus the next one we have is 0.9759 multiplied by 22.1 over 100 also. And then now the last one, which is 207.9766 multiplied by 52.4 divided by 100. So this is given me a relative atomic mass of 112.8415793. So as we are able to see the masses, they are given to four decimal places, so we can as well leave it as 112.8416 atomic mass unit. So this is going to be it. We are good. Is that okay? Okay.
What's the limit?
So I haven't even. Oh, the question. Calculate the average atomic mass and identify the element. What's the value that I've calculated? I don't know if you've seen that.
It was 112 point something going there, but 1.7.187
Okay.
something.
112, right?
Yes.
So we'll go now on the periodic table. We check something with a relative atomic mass of 112. Let me check out on the periodic table. So from the periodic table, we have got 112.411. So if that is the value, then that should be cadmium. This one has got a molar mass of 112.411 grams per mole. Because apart from this one, the next one has got a molar mass of 114.81, and this is too much high. So we expect it to be this one if I've punched rightly on the calculator finding the relative atomic mass. Okay. D. Given that the average atomic mass of silicon is 28.09, complete the following table. The average mass is 28.09. Now, we don't have the abundance. We also don't have the mass here. One thing that you need to know about abundance is that the abundance is a percentage. So it should always give you 100% when you add all the masses of all the elements in that compound. Okay, it should give you what? Should give you 100%. As a decimal, it should give you a 1. So we're going to add. Now, since this is 4.7, definitely this should be a percentage, okay? Because if it was just a mere decimal, we can't have a number above 1. So we are going to add the 4.7 plus 3.09. That answer that we find, we are going to remove it from 100. So therefore, this is going to be 95.21. That will be the percentage of the first one. Now to be able to find this value which is missing, which is the mass in this case, we are going to say the relative atomic mass, which is 28, say 28.09, is going to be equal to this mass multiplied by the abundance. So that is 27.98 multiplied by the abundance, which is 95.21, and then divide that by 100 because this is a percentage. And then plus the next mass, which we don't multiply by the abundance, which is 4.7, also divide by 100. And then the next mass, which is 29.97, multiply by the abundance, which is 3.09, divide also by 100. Are we okay?
Yes.
Okay. So just get to punch this one out. So let me write first I'm going to punch this and this on the calculator direct because you can find that. So 27.98 multiplied by 95.21 divided by 100. And then plus I also go to the other side, which is the 29.97 multiplied by 3.09, then divide by 100. So this just that, so we're going to have 28.09 being equal to, just if we add this and this, we are going to get 27.565831. And then plus we are going to have,
So
yes,
is this the 90? Is it 95.21?
yes, 95.21.
Is it not supposed to be 92.21?
Oh, that's the one you found?
The abundance percentage.
Oh yeah, you are right. So I might have punched a 2 here instead of 4, because 4 plus 3 is a 7, so it's supposed to be 92. So that's the one we're going to also use here. So this value then, if we get to add, is going to give us 26.726431. And then that is going to be plus this 4.7 over 100, that is going to be 0.047, and then multiplied by m. I'll take this value this side, so we are going to have 28.09 minus that value. That is going to give us 1.363569 being equal to 0.047m. So when we want to remain with now the m, divide both sides by 0.04. Therefore the mass 0.047. The mass is going to be 29.012. This one is in atomic mass unit. So this is going to be the value which is missing there. We are good there, right?
Yes.
Okay. So question E. Nitrogen is made up of two isotopes, nitrogen 14 and nitrogen 15. Given nitrogen 14 atomic mass of 14.007, what is the percentage abundance of each isotope? Okay, what's the percentage abundance of each isotope? So we have got nitrogen 14 and also nitrogen 15. Now, from here, the only thing that we've been given, just a moment, I admit. Okay, so the only thing that we've been given is nitrogen's atomic mass. So we've been given the relative atomic mass as 14.07. Want to calculate the abundance of these. So for this case, I'm going to take this one, just the 14 given as its mass, the other one, the 15 given as its mass. Now the relative atomic mass is given as 14.007. Now, if the abundance for nitrogen 14 is X, the abundance for nitrogen 15 is going to be 1 minus X. Like we know that the abundance should add up to 1, right? 1 is the same as 100%. So if 1 is giving us X, what should be the other value, such that when we add them, they give us a 1. So the other one is going to be 1 minus X. That's why I've taken that as the abundance. If I want, I can say if this nitrogen 15 is Y, then nitrogen 14 is going to be 1 minus Y. So I'm going to say atomic mass, which is given as 14.007, is going to be equal to mass 1, which is 14, multiplied by the abundance, which is x, plus mass 2, which is 15, multiplied by the abundance, which is 1 minus x. So this will give us 14.007. That will be equal to 14x plus 15 times 1, that is 15. 15 times x, that's 15x. So we're going to take now the 15 the other side. So it will be negative, right? So we're going to have 14.007 minus 15. That will be negative 0.993. And here we're going to have 14x minus 15x, which is going to be negative x. So the x will divide. So that means that x is going to be 0.993. What does this tell us? This tells us, remember, x was representing for nitrogen 14. The abundance for nitrogen 14 is going to be, now this is a decimal, convert to a percentage, multiplied by 100%. So it's going to be 99.3%, meaning that nitrogen 15, the abundance is going to be 100 minus that value. Okay, so we'll say 100 minus the 99. That is going to give us about 0.7%. That will be the abundance of the other one. Are we okay?
Yeah, we're okay.
Okay. Question 2. Glycerol given as C3H8O3 is solid in drugstores as glycerin and is commonly found in soaps and shampoos. What is the molar mass of glycerol? We have got C3H8O3. Depending on the periodic table that you are going to be given, you can use the mass of oxygen. Some will be 15.994, others will be 16. Let me use 16, a whole number, but use the mass from the periodic table that you are going to be given. We have got 8 hydrogens. I'm going to multiply by 1, but others you'll find that it is 1.008. Then I've got 3 carbons. I'm going to use the molar mass as 12. Others, of course, is going to be different. Okay, depending on the periodic table that you have. So let's get to punch this. 3 multiplied by 16 plus, we have got 8, and then plus we have got 3 multiplied by 12. That is going to give us 92 grams per mole. What is the mass in grams of 1 mole of glycerol? The mass in grams of 1 mole. Now, just from the molar mass, this is the mass per mole. So for part B, the mass in grams of 1 mole of glycerol is going to be 92 grams. How many molecules are in 1 mole of glycerol? Now, 1 mole of anything, we know that that
So
is what?
it has stopped showing here.
Oh, you are not seeing what I'm writing.
It has been stuck. Okay. Yeah, now it has started.
Okay. So, on part C, how many molecules are in 1 mole of glycerol? So we've said for anything, 1 mole of anything is always equal to 6.022 times 10 to the power 23 molecules, ions, particles, and also just everything. So that is going to be the answer. We are good on that one. It,
On the grams, what did you find?
it's 92. What is the mass in grams of 1 mole? So 1 mole of this is 92 grams. So you just get from the molar mass. Okay. And then for part D, how many grams are in 0.217 moles? Now you already know that you have got 92 grams per mole. So simply multiply by the moles given, 0.217 moles. You are going to find how many grams are there. So these two values are going to cancel out. What do you get when you multiply if you have got a calculator near? 92 by 0.217. That will be 19.964 grams. So that will be the mass. We are good with question 2.
Yes.
Question 3. Ammonia is the active ingredient in many kitchen cleansers. How many atoms are in one molecule of ammonia? How many atoms are in one molecule of ammonia? Okay. Remember what we are talking about is in you want to find how many atoms are going to be in one molecule. This is also something that is a bit of trick. So maybe something that I should be able to mention is that one mole of anything is equal to 6.022 times 10 to the power 23 molecules. Okay, it is also equal to 6.022 times 10 to the power 23 atoms. What does this tell you? This tells you that the number of molecules of a substance is equal to the number of atoms, as long as you have got the same moles. Okay, so how many atoms are in one molecule of ammonia? Then you are going to have, you expect to have, now if you use this relation, let's get to just go directly with the formula. If this is one atom of one molecule of ammonia, the number of atoms that we're able to see direct from here, we have got 4 of them. So for this one, we can just go direct. But the relation that I wanted to give is that molecules and atoms, they're all, that is in comparison to a mole, so I can't use that one. That's why I've changed. So in one molecule of ammonia, you have got 4 atoms, all right? And then how many atoms are in one mole of ammonia? Now, one mole of ammonia contains 6.22 times 10 to the power 23 atoms. So for part B, this is going to be the answer. Now, and then for part 3, 3.4 grams of ammonia. So the first thing you need to determine are the number of moles of ammonia, that is mass, which is the 3.40 grams, divided by the molar mass. I've got 3 hydrogens. Nitrogen has got a molar mass of 14. 14 plus 3, that is 17 grams per mole. So this is going to give us 3.4 divided by 17, and that is 0.2 moles. Now you already know that 1 mole has got 6.022 times 10 to the power 23 atoms. Now how about 0.2 moles? That's what you want to find now, x. So therefore x is going to be 0.2 multiplied by 6.022 times 10 to the power 23. And that is going to give us 1.2044 times 10 to the power 23 atoms. So that is going to be it. We are good with this also.
Yes.
Okay. Okay, the next part B. How many molecules are in the following? 1.29 times 10 to 23 hydrogen atoms. Now I want to determine how many molecules of hydrogen fluoride. Now you can clearly see that when you have got one molecule of hydrogen fluoride, how many atoms do you have? Or actually, we are. Let me just ask that. If you have got one molecule of hydrogen fluoride, how many atoms do you have? This one. How many atoms are there?
two.
You have got two atoms. Now, we want to find how many moles are in this number of atoms. Okay, so we know that one mole is 6.022 times 10 to the power 23 atoms. Now, we want to find how many atoms are going to be in 1.29 times 10 to the power 24 atoms. To find x is simply going to be this value which is here divided by 6.022 times 10 to the power 23 atoms. The 23 can go into 24, we're going to remain with a 10. And so from here, all we are going to do is get the 1.29, we divide that by 6.022. The answer that we get to multiply by 10. So that is going to give us 2.14 moles. So that is going to be it. And then the next one, how many moles are in 7.36 free oxygen atoms? Okay, free oxygen atoms. Same, we know that one mole is 6.022 times 10 to the power 23 atoms. Now, how many moles are going to be in 7.36 times 10 to the power 23 atoms of oxygen? So, all we do is divide this value by 6.022 times 10 to the power 23 atoms. Now, the 23 and the 23 will cancel out. So, all we are going to have is 7.36 divided by 6.022. And that is going to give us the answer here is supposed to be 1.22 moles. So that is it for that question. Now let's have part 3. How many moles are in 3.28 times 10 power 23 sodium atoms? Okay, in sodium chloride, same. One mole is the same 6.022 times 10 to the power 23. Doesn't matter what you're talking about, atoms. Now I want the number of moles present in 3.28 times 10 power 23 atoms. So simply divide this value by 6.022 times 10 to the power 23 atoms. Power 23 will cancel out. So the number of moles therefore is going to remain 3.28 divided by 6.022. That is going to be about 0.527 moles. Part C. Ammonia and oxygen react to form nitrogen and water. Are we okay with those are on top?
Yes.
Okay. Ammonia and oxygen react to form nitrogen and water. Write a balanced equation for the reaction. We have got ammonia, Na3, which reacts with oxygen, which is a diatomic gas. This forms nitrogen, which is also diatomic, and water, which is H2O. So a balanced equation, we have got two oxygens here. So we're supposed to also have two oxygens. So I'm going to put a 2 here. That makes the hydrogens 4. So now to balance the hydrogens is going to be tricky. You see that? So the first thing that I'm going to balance is the ammonia. We have got two nitrogens, so I'm going to put a 2 here to balance the nitrogens. This makes the hydrogens to be 6. Okay. So to balance the hydrogens, which are 6, I'm going to put a 3 here. Now if I put a 3 here, that is going to make how many? Okay, 6 hydrogen, 6. The oxygens are now 3. Now again, for me to balance this one which is here, I'll balance it by multiplying by 3 over 2. Actually, for when you're dealing with equations that have to do with combustion, you can balance with half with the fractions. Now you can see it is tricky if I balance with a fraction, right? So I'm balanced with a fraction because these 2 in the denominator can cancel with these 2. And then I'm going to remain with 3 oxygens, which balances with 3 there. If I don't want to have a fraction, I'll multiply everything by 2. So 2 times the ammonia, that is going to be 4 ammonia. And then plus, we are going to have 3 oxygens like that. Then the other side, we are going to have 2 nitrogens. And then plus 6 water molecules like that. So 4 hydrogens, 4 hydrogens. We have got 12 hydrogens, 12 hydrogens. Got 6 oxygens, 6 oxygens. So that's the balance equation. You can write this. You can write this. We are good with this one.
Yes.
Okay.
This method only applies in combustion.
Mostly when you're talking about organic compounds which have to do with burning in oxygen, you can balance with half fraction numbers. Okay, let's consider now how many molecules of oxygen are needed to react with 8 moles of ammonia. How many moles of oxygen are needed to react with 8 moles of ammonia. Now from the balance equation we've seen that 4 moles of ammonia, let me actually write it in another form. So we're going to say number of moles of ammonia divided by 4 is equal to number of moles of oxygen divided by 3. So now we've been given 8 moles of ammonia. So that would be 8 divided by 4 is going to be equal to n of oxygen divided by 3. So this is going to give us a 2. Okay, that's 2 multiplied by 3. So we need 6 moles of oxygen to react with 8 moles of ammonia. Okay. So let's work out the next one. How many grams of nitrogen gas can be produced when 6.5 grams of oxygen react? Want now the grams of nitrogen. So from the balance equation, what are we burning when 6.5 grams of oxygen react? So mass divided by the molar mass of oxygen. Now oxygen has got a coefficient of 3, right? So I'm going to put a 3 in the denominator. Should be equal to mass divided by the molar mass of nitrogen. Now nitrogen has a coefficient of 2. Remember I multiplied the equation by 2. Okay, so we are going to put 2 in the denominator. What are we burning? 6.5 grams of oxygen. So that will be 6.5 divided by 3 multiplied by the molar mass for oxygen, 16 times 2, that is a 32. Use the one that will be given according to the periodic table that you have. And then we're going to have mass, which we want divided by molar mass of nitrogen. Nitrogen is the atomic, and each is 14. So 14 times 2, that is a 28. So therefore the mass is going to be multiply these two values, 2 times 28 times 6.5. And then we are going to divide by this term here, which is 3 multiplied by 32. So that is going to give us 2 times 28 times 6.5. Then divide that by 3 multiplied by 32. So that is going to give us about 3.79 grams of nitrogen gas to be produced. This is okay?
Yes.
Okay. And then how many grams of water can be produced from the reaction of 34 grams of ammonia? Now we're rating ammonia with water. I can actually just use the same one which is given. So mass of ammonia divided by 2, the molar mass of ammonia, is going to be equal to the mass of water divided by 3, the molar mass of water. So the mass of ammonia that we are burning, that is 34 grams, divided by 2, the molar mass for ammonia. How did we determine? Nitrogen is 3, nitrogen is 14 plus 3, that is 17. That will be equal to the mass of water divided by 3, the molar mass for water is 18. So therefore the mass is going to be, we multiply these to 34 times 3 times 18, then divide by this 2 multiplied by 17. Let's see what we get. 34 by 3 by 18, then divide that by 2 multiplied by 17. That is going to give us 54 grams of water to be produced. We can consider question 4. Okay. For question 4, you can allow me just to end on A, and then we're going to complete the B, C, D other questions. Sodium nitrite. Sodium nitrite is a controversial food preservative. Okay. Added to processed meat and thought to form cancer causing compounds. Now we want to write the formula for sodium nitrite. Now first we need to know what the symbol for a nitrite is. A nitrite, where is it even? This one here is given as NO. It's actually a minus. It's NO2, the minus. So that's a nitrite. We also have a nitrate. So if this was nitrate with an A, that is NO3. This one has a charge of positive 1. So that's the difference between these two. This one is a positive. Nitrite has got one oxygen less than a nitrate. So just put sodium in front. So the charge is going to go. That's sodium nitrite. What is the mass percentage of each element in sodium nitrite? So we need just to calculate the total mass of this compound. So sodium, the mass on the periodic table is 23. Nitrogen is 14. We have got two oxygens and each is 16. So 2 times 16, which is a 32, you add 14, also add a 23. That is going to give us a 69. So if you want to find the percentage of sodium, it's going to be 23 over 64 times 100. This is 100%. 23 divided by 64 times 100, that is going to give us about 35.9%. Find the percentage of nitrogen is 14 out of 64. And that multiplied by 100%. That is going to give us about 21.9%. Find the percentage of oxygen. The molar mass of oxygen is 2 times 16, which is 32. Then divide that by 64, multiply by 100%. So that is 32 divided by 64. That is going to give us 50%. So this is it for question A of part question 4.